What does a city of galaxies look like while it's being built? Webb just caught 5 young galaxies tangled together in the fog of the early universe. How do they assemble that fast? Why is fragile dust showing up tens of thousands of light years above a galaxy's disk? Webb sees it surviving a 100 million year superwind into the halo. If halos keep dust, do galaxies breathe differently than we thought? And can we actually watch a planet eat? A newborn giant just flashed a hydrogen heartbeat, gas falling in, growth in real time. That's the core. But don't blink. 2 nearby Earth-sized worlds bright enough for atmosphere work. Jupiter's last missing auroral footprint finally lighting up. Newborn star jets resolved at the galaxy's edge. Fomalhaut's debris ring acting like a crime scene for ancient planets. A possible bridge from JWST's little red dots to the rare BlueDOG powerhouses. And a Kepler planet that didn't survive a pixel-level audit. This is AstroNEWS Weekly. Dive in. JWST Quintet 5 galaxy pileup at redshift approximately 6 point. Webb has caught a city of galaxies under construction less than 1 billion years after the Big Bang. At least 5 compact galaxies are tangled inside a shared halo, and the field lights up in H alpha and O3, where stars are forming at a furious pace. Between the galaxies, faint bridges of gas arc like stretched taffy, evidence that gravity is stripping and sharing material as the system comes together. This matters because a 5-way merger this early means assembly was fast and messy. Such collisions can open escape routes for ionizing light, spread heavy elements far from their birth clouds, and set the stage for rapid black hole growth. Next up is hard kinematics. NIRSpec will lock redshifts and velocities to see who is inbound, who is outflowing, and how turbulent the halo really is. Simulations will try to reproduce the clumpy gas and the measured star formation rates. If they fail, our timeline for early growth needs edits. If they succeed, we gain a template for spotting more proto-cities across the sky. Warm dust in the halo of the starburst galaxy Makani. Webb has traced warm dust and complex molecules tens of thousands of light years above the disk of Makani, out in the thin circumgalactic halo. Using mid-infrared sensitivity, the team followed faint pH features and dust continuum carried by superwinds launched by clustered supernovae and hot young stars. Dust is fragile, yet the maps show grains surviving a ride of roughly 100 million years, with temperature and composition changing with height. Outflows are not just gas hoses. They are conveyor belts for solids that cool halos seed molecules and provide surfaces where chemistry happens. This reshapes the galactic breathing cycle. If dust persists in halos, they cool faster, clouds condense, and some material falls back to refuel the disk. Dusty halos also redden background light and can bias measurements if ignored. Next steps pair these maps with ALMA to get gas to dust ratios and grain sizes versus radius, and to track where pHs are processed or destroyed. The goal is a closed-loop diagram of how galaxies launch, process, and refuel. AB Aurigae BH alpha detection, a planet still feeding. We have seen rings and gaps for years, but this time we see feeding. With the MUSE instrument on the Very Large Telescope, astronomers detected H alpha emission at the position of AB Aurigae B, hydrogen glowing as gas falls onto a forming giant planet. The shape of the line resembles an inverse P Cygni profile, which is a hallmark of infalling material. Combine the line flux with the local continuum, and you can estimate an accretion rate, a direct measure of growth rather than an inference from dust structures. The geometry points to streams funneled from the disk to the planet along pressure gradients. Only a few systems show protoplanets in H alpha, so AB Aurigae B becomes a benchmark for how fast giants assemble and how they carve gaps. Next, the team will run time series spectroscopy to catch accretion bursts, while Webb maps warm dust and molecules and ALMA traces cooler gas flows. If the streams line up, we will see where gas comes from, where it lands, and how much ends up on the planet. Pismis 24 in the Lobster Nebula, glittering glimpse of star birth. Along a ridged wall of dust, newborn massive stars are carving their own nursery, and Webb resolves the erosion front in fine detail. Bright rims mark ionization, and deeper inside point like protostars pierce the haze with narrow jets. The hottest members blaze far above the sun in temperature and drive winds that clear cavities while compressing nearby gas. That compression can ignite new waves of star formation along the edges even as feedback shuts it down elsewhere. This is a classroom for feedback physics. Massive stars dominate their neighborhoods by injecting energy and forging heavier elements, and by setting the initial conditions for planetary systems exposed to intense ultraviolet radiation. Next comes integral field spectroscopy to measure shock speeds, densities, and chemical fingerprints along the rim. With proper motions, we can watch the ridge retreat and estimate how many new stars it leaves behind, turning a still into a slow time lapse of a working nursery. Two Earth-sized worlds around the nearby K-dwarf TOI 2322. Tests flagged two cleanly repeatable transomed, a bright quiet K-type star, and ground spectrographs moved quickly to confirm sizes and orbits. Together, transit depths and stellar wobbles set density, and early numbers point to rocky worlds rather than puffy mini-Neptunes. Short orbital periods make this system a workhorse for atmospheric studies. Frequent transits allow stacking many events to search for very thin envelopes with sodium, potassium, or carbon dioxide, or to place tight upper limits if no atmosphere is present. Why this matters is simple. Many Earth-sized finds are poor atmospheric targets because hosts are faint or orbits are long. Here the host is bright and calm, and the cadence is fast, so the system can anchor studies of photoevaporation and climate on small worlds around K-dwarfs. Next steps: tighten masses with sustained radial velocity work, look for transit timing variations that hint at unseen companions, and schedule Webb visits to probe for ultron atmospheres. Juno confirms the missing Callisto auroral footprint. Jupiter's polar lights carry signatures of its moons where currents stream along magnetic field lines and slam into the atmosphere. We have long seen the footprints of Io Europa and Ganymede. Now analysis of Juno data confirms the last one, Callisto. The detection relies on a fortunate geometry from a 2019 PAHs and on refined models and multi-sensor measurements. Callisto orbits far out in a tenuous environment, so its electrical signature is faint, which explains the long delay in finding it. Completing the set advances comparative magnetosphere science by showing how surfaces and tenuous atmospheres control current flow. The result informs energy input at ocean worlds and provides a laboratory for understanding star-planet magnetic interactions in exoplanet systems. Next, the team will coordinate Juno ultraviolet observations with ground-based telescopes to time-track the footprint and to link brightness to plasma conditions and moon environments, building a kind of space weather forecast for a giant magnetosphere. First resolved protostellar jets in the outer Milky Way with ALMA. In the metal-poor outskirts of the Milky Way, ALMA has resolved the classic bipolar outflows of a newborn star for the first time so far out. Shock traces such as carbon monoxide and silicon monoxide show chemistry that differs when heavy elements are scarce, yet the collimation and velocities look textbook. This suggests the magnetocentrifugal engine that flings gas off disks works even in lean environments. The outer disk then becomes a local stand-in for early universe conditions where metallicity was low, and yet stars and disks still formed efficiently. The impact is direct. If jet physics is robust to metallicity, then the recipe for building stars and the disks that spawn planets scaled across eras, anchoring models of how quickly galaxies lit up the dark. Next is a wider ALMA census to tie metallicity to outflow momentum and disk lifetimes, and to combine with Webb and large optical telescopes for a multi-phase jet budget across gas dust and the magnetic scaffolding. Fomalhaut's warped ring and the forensics of ancient planets. The famous debris ring around Fomalhaut is not only offset from the star, it is subtly warped, and its eccentricity changes with distance. New modeling shows this is the pattern expected when one or more planets sculpt the inner edge more strongly than the outer regions. Dynamics turns shape into evidence. A planet on a slightly tilted and eccentric orbit can pump the inner edge into a tighter, more eccentric track while leaving the far side looser, producing a gradient and a gentle warp. You do not need to see the planet to weigh it. Its gravity writes a pattern in dust. This is exoplanetary archaeology. When direct imaging comes up empty, the ring preserves a dynamical record of missing actors and ancient events. Next, deeper ALMA and scattered light imaging will hunt for resonant clumps that act as smoking guns. Guided by those patterns, next-generation coronagraphs will take another shot at direct detection. From little red dots to BlueDOGs, a possible evolutionary bridge. A new study links JWST's compact dust-buried little red dots near cosmic dawn to the rare hyperluminous BlueDOG galaxies at redshift around 2 to 3. Two very different looks, maybe one growth track separated by time and feedback. A recently observed BlueDOG shows a huge broad H-alpha line under heavy dust, yet a surprisingly blue ultraviolet excess that could be scattered active nucleus light or a peaking starburst. Its spectral energy distribution mirrors traits inferred for little red dots scaled forward. If the red dots are Act 1, then BlueDOGs could be Act 2 as feedback punches holes in the cocoon and some light leaks out. An evolutionary bridge reframes quasar ignition as a morphing process rather than a jump. It lets us test physics nearby and export those lessons to the most distant systems. Next steps include polarimetry to confirm scattered light, time domain monitoring for variability, and larger ALMA and Webb samples to see if numbers, masses, and duty cycles line up with the proposed timeline. KOI 1755 reclassified the planet that was not. A careful pixel-level audit shows the Kepler signal tagged as KOI 1755 does not belong to the target star. It comes from a background eclipsing binary blended into the spacecraft aperture. So the shallow planet-like dip was a diluted stellar eclipse. The team used pixel response functions and centroid shifts to trace the signal to a faint nearby source and reconstructed the true deep eclipse once the background light was isolated. Kepler's target pixel files always held the answer. They needed the right tools. Cleaning catalogs sharpens planet occurrence rates and protects scarce follow-up time. It also sets a standard for tests and future missions working in crowded fields. Start with statistical vetting and escalate to pixel forensics when the flags pile up. Next, the same pipeline will be applied to other ambiguous candidates and cross-matched with Gaia and adaptive optics imaging to preempt false positives. The goal is fast and transparent corrections that keep the science honest. That's the wrap on this week's Astro News. If it helped make the cosmos make sense, like the video, share it, and subscribe. Your support keeps this going. Check out the Anantam and Beyond merch store at anantamandbeyond.com.